Can a person who is blind come to see through her tongue? Can a baby be born without ears? What is it like to have the smell of a dog? And what does any of this have to do with airplane pilots or Westworld or Potato Head? Welcome to Inner Cosmos with me, David Eagleman. I'm a neuroscientist and an author, and my fascination for a very long time has been how brains perceive reality. Because the strange part is that we're not seeing most of the action that's going on out there. So today we're going to dive into that, and we're going to see how we might expand our perception. We're built out of really small stuff like DNA, and we're embedded in a very large cosmos, and we're not particularly good at perceiving reality at either of those scales. And that's because we've evolved to deal with reality at this very thin slice in between at the level of rivers and apples and rabbits and stuff like that. But even here at our level of perception, we're not seeing most of the action that's going on. So take, for example, the colors of our world. So picture the reds and blues and greens and purples. These are light waves that bounce off objects and hit these specialized receptors at the back of our eyes. And then we perceive these colors. But we're not seeing all the light waves that are out there. In fact, what we see is less than a 10 trillionth of the light waves out there. So if you look at what's called the electromagnetic spectrum, you have radio waves and microwaves and X-rays and gamma rays. All these are light. They're just different frequencies. These are passing through your body right now, and you're completely unaware of them because your biology doesn't come with the right receptors to pick those up. They are light, but they're not visible light. There are thousands of cell phone conversations passing through you right now, and you're completely blind to them. Now, it's not that these other wavelengths of light are inherently unseeable. Snakes include some infrared light in their reality, and honeybees include ultraviolet light in their view of the world. And of course, we build machines in the dashboards of our cars to pick up on signals in the radio frequency range. And we build machines in hospitals to pick up on the X-ray range and so on. But you can't sense any of these things by yourself, at least not yet, because you don't come equipped with the proper sensors. Now, what this means is that our experience of reality is constrained by our biology. And that goes against this common sense notion that our eyes and our ears and our fingertips are just picking up on the objective reality out there. Instead, what this means is that our brains are sampling just a little bit of the world. Now, across the animal kingdom, different animals pick up on different parts of reality. So take the tick. It's blind and deaf. And in its little world, the important signals are temperature and body odor, butyric acid. And that's all it picks up on. And that's how it constructs its reality. For a fish called the black ghost knifefish, its sensory world is all about electrical fields and the perturbations of those fields when it's passing a rock or another creature. And that's all it's picking up on. For the echolocating bat, its reality is constructed out of air compression waves that bounce off objects and come back to them. So for these different animals, that's the slice of their ecosystem that they can pick up on, and that's all they're seeing. And we have a word for this in science. This is called the umvelt, which is the German word for the surrounding world. Now, every animal is very limited in the umvelt that it can pick up on. But presumably every animal assumes that its umvelt is the entire objective reality that's out there. Because why would you ever stop to imagine that there's something beyond what you can sense? Instead, we all accept reality as it is presented to us. So let's do a consciousness raiser on this. Imagine that you are your family dog. And your whole world is about smelling. So you've got this long snout that has 200 million scent receptors in it. And you have wet nostrils that attract and trap scent molecules. And your nostrils even have slits so you can take these big nosefuls of air. You have floppy ears to kick up more scent. Everything is about smell for you. So one day, you stop in your tracks with a revelation and you look at your human owners and you think, what is it like to have the pitiful little nose of a human? What is it like when they take a little feeble nose full of air? How can a human not know that there's a cat 100 yards away or that their best friend was on this very spot 6 hours ago? But because we're humans and we've never experienced that world of smell, we don't miss it and we don't even think about it because we are firmly settled into our umvelt. We don't feel like there's a black hole of smell that we're missing there. We think we've got the whole world. But the question is, do we have to be stuck in the umvelt into which we were born? So as a neuroscientist, I've always been interested in the way that our technology might allow us to expand our umvelt and how that's going to change the experience of being human. So we're already quite good at marrying our technology to our biology. You may know this, but there are hundreds of thousands of people walking around with artificial hearing and artificial vision. The way this works, for example, with artificial hearing is you have a microphone and you digitize the signal and you put an electrode strip directly into the inner ear. Or with artificial vision, you have what's called a retinal implant where you take a camera and you digitize the signal and you plug an electrode grid directly into the back of the eye and the optic nerve. Now, as recently as 25 years ago, there were a lot of scientists who thought these technologies were never going to work. Why? It's because these technologies speak the language of Silicon Valley and zeros and ones, and it's not exactly the same dialect as our natural biological sense organs. But the fact is that these technologies work. The brain figures out how to use the signals just fine. Now, how do we understand that? The key to understanding this requires diving one level deeper. Your 3 pounds of brain tissue are not hearing or seeing the world around you directly. It's not that your eyes are piping in light or your ears are piping sound in. Instead, your brain is locked in a crypt of silence and darkness inside your skull. All it ever experiences are electrochemical signals that stream in along different data cables. That's all it has to work with are these little electrical spikes and chemical releases. It's just a world of spikes running around in darkness inside there. And in ways that we're still working to understand, the brain is shockingly good at taking these signals running around and extracting patterns. And to those patterns, it assigns meaning. And with that meaning, you have subjective experience. So the brain is an organ that converts sparks in the dark into a picture show of your world, all the hues and aromas and emotions and sensations of your life. These are encoded in trillions of signals zipping around in the blackness. So, when you watch a beautiful screensaver on your computer screen, that's just built out of zeros and ones and transistors. And it's somehow the same thing that's happening with your experience of the world. Let's understand this just a little bit more. Imagine that you traveled over to an island of people who were all born blind. So they all read by braille. They feel tiny patterns of inputs on their fingertips. So you watch them read a book and they're brushing over the small bumps with their fingers, and you watch them laugh and cry at the book they're reading. And you might wonder, how can they fit all that emotion into the tip of their finger? So you explain to them that when you read a novel, you aim these spheres on your face towards visual patterns of lines and curves on a page. And each of your eyes has a lawn of cells that catch photons. And in this way, you can register the shapes of the symbols. And you tell them that you have memorized a set of rules by which different shapes on the page represent different sounds. So for each squiggle that you detect with your eyes, you recite a small sound in your head, imagining what you would hear if someone were speaking that out loud. And so the resulting pattern of neurochemical signaling makes you laugh or cry. You couldn't blame the Islanders for finding your story difficult to understand. How do you fit all that emotion into two spheres on your head? Okay, so you or they would finally have to allow something, which is that the fingertip or the eyeball is just the peripheral device that converts information from the outside world into spikes in the brain. And then the brain does all the hard work of the interpretation. You and the Islanders would break bread over the fact that in the end, it's all about the trillions of spikes racing around in the brain, and that the method of entry simply isn't the part that matters. Because your brain doesn't know and it doesn't care where it gets the data from. Whatever information comes in from the outside, it just figures out what to do with it. And this is a very efficient kind of machine. It is essentially a general purpose computing device. It just takes in everything and it figures out what it's going to do with it. And in my work, I've proposed that this frees up Mother Nature to tinker around with different sorts of input channels. So I've argued in my talks and books and papers that we can send information into the brain via unusual pathways. And I call this the pH model of evolution. And I don't want to get too technical here, but pH stands for potato head. And I use this name to emphasize that all these sensors that we know and love, like our eyes and our ears and our fingertips, these are merely peripheral plug-and-play devices. You stick them in and you're good to go, just like with a potato head where you attach these devices. The brain figures out what to do with the data that comes in. And by the way, when you look across the animal kingdom, you find lots of interesting peripheral devices. So snakes have heat pits with which they detect the infrared light. And the black ghost knifefish has electroreceptors up and down its body. That's how it detects the changes in the electrical fields. And there's an animal called the star-nosed mole, which essentially has this nose with 22 fingers on it, and it moves around through its three-dimensional tunnel system and feels around and constructs a model of its world that way. And many birds and cows and insects have specializations so that they can feel the magnetic field of the planet. This is called magnetoreception, and they navigate that way. So the idea with the potato head model is that Mother Nature doesn't have to continually redesign the brain every time she introduces some new peripheral device. Instead, with the principles of brain operation already established, all she has to do is worry about designing new peripheral devices to pick up on new information from the world. So in the same way you can plug an arbitrary nose or eyes or mouth into potato head, likewise, nature plugs all kinds of instrumentation into the brain for the purpose of detecting these energy sources in the outside world. Now, the idea of looking at our peripheral sensors like individual standalone devices might seem bizarre because, after all, aren't there thousands of genes involved with building these devices? And don't these genes overlap with other pieces and parts of the body? Can we really look at the nose or the eye or the ear or the tongue as a device that stands alone? So I started studying this question because I thought, if the potato head model is correct, wouldn't that suggest we might find switches in the genetics that lead to the presence or absence of a peripheral device? And as it turns out, that's precisely what can happen. So for example, some babies are born completely missing a nose, and they also lack the nasal cavity and the whole system for smelling. This is called arrhynia. Now, these kind of mutations, they seem startling and difficult to fathom, but in our plug-and-play framework, arrhynia is predictable. With a slight tweak of the genes, the peripheral device simply doesn't get built. Or consider other babies who are born normal, but they have no eyes. This is called anophthalmia. And others are born without tongues. Some babies are born without ears. That's called anotia. Some children are born without any pain receptors. And more generally, others are born without any touch receptors. This is called anaphia. And so when we look at these situations, it becomes clear that our peripheral detectors unpack because of specific genetic programs. And if you have a minor malfunction in the genes, that can halt the program. And then the brain just doesn't get that particular data stream of information from the world, whether that's smell molecules or photons or air compression waves or touch or whatever. For me, the lesson that comes together here is that nature designs ways of extracting information from the world, and these unpack with their own little genetic instructions. Now, what this implies is that there's nothing really fundamental about the devices that you and I come to the table with, our eyes and our ears and our nose and our fingertips. It's just what we've inherited from a complex road of evolution. But that particular collection of sensors might not have to be what we stick with, because the brain's ability to decode different kinds of incoming information implies the crazy prediction that you might be able to get some sensory cable going into the brain to carry a different kind of sensory information. For example, what if you took a data stream from a video camera and converted that into touch on your skin? Would the brain eventually be able to interpret the visual world simply by feeling it? And this is the stranger than fiction world of sensory substitution. Sensory substitution refers to the idea of feeding information into the brain via unusual sensory channels, and the brain just figures out what to do with the information. Now, that might sound speculative, but the first paper demonstrating this was published in the journal Nature in 1969. There was a scientist named Paul Bocchi-Rita, and he put blind people in a modified dental chair, and he set up a video feed. And he would put something in front of the camera, and then the person would feel that poked into their back with a grid of solenoids. So if he put a coffee cup in front of the camera, they would feel the shape of a coffee cup in their back. Or he puts a telephone in front of the camera and they feel a telephone in their back. And amazingly, people who were blind got pretty good at being able to determine what was in front of the camera just by feeling it in the small of their back. So Bocchi-Rita summarized his findings by saying, quote, "The brain is able to use incoming information from the skin as if it were coming from the eyes," end quote. The subjective experience for the blind people who were feeling this in their back was that visual objects were located out there instead of on the skin of their back. In other words, it was something like vision. And think about it this way: when you're at the coffee shop and you see your friend waving at you across the way, the photons from your friend are impinging on your photoreceptors in your eye, but you don't perceive that the signal is at your eyes or in your brain. You perceive that your friend is out there waving at you from a distance. And so it goes with the users of Bocchi-Rita's modified dental chair. They were perceiving the object out there. Now, amazingly, while Bocchi-Rita's device was the first to hit public consciousness, it was not actually the first attempt at sensory substitution. On the other side of the world, at the end of the 1890s, a Polish ophthalmologist developed a crude device for people who were blind. He put a single photocell on the forehead of a blind person, and the more light that hit it, the louder a sound would be in the person's ear. So based on the sound's intensity, the blind person could tell where there were lights or where there were dark areas. Unfortunately, the whole device was very large and heavy, and of course, it was only 1 pixel of resolution, so it never got any traction. But in 1960, another group in Poland picked up the ball and ran with it. They recognized that hearing is critical for the blind, so they turned to passing in the light information via touch. They built a helmet that had all these vibratory motors in it, and they essentially drew the images on the head. And blind participants were able to move around in these specially prepared rooms that were painted to enhance the contrast of the door frames and the furniture edges. It worked. Unfortunately, it was also heavy and would get very hot, and so the world had to wait. But the proof of principle was starting to emerge. Now, why did these strange approaches work? It's because inputs to the brain, whether that's from photons of the eyes or air compression waves at the ears or pressure on the skin, they're all converted into the common currency of electrical signals. So as long as the incoming spikes carry information that represents something important about the outside world, the brain will learn how to interpret it. The vast forests of your brain cells in the dark, they don't care about how the spikes get there. They just do their work on it. Now, there have been all kinds of incarnations of sensory substitution for the blind. One, also from the 1960s, is called the sonic glasses. It takes a video feed right in front of you and turns that into a sound landscape. So as things move around and get closer and farther, it sounds like a cacophony. But after some time, blind people start getting really good at understanding what is in front of them just based on what they're hearing through their ears. And the best example of this is a program that you can download on your cell phone called The Voice. Note that the three middle letters are OIC. Anyway, this is developed by an engineer named Peter Meyer in the Netherlands. And it started as a bulky project, but it can now be downloaded on your phone. You point your phone camera at things, and the program converts what the phone sees into sounds. The app is amazing, and you can download this onto your phone and start walking around in the world with it and really understand what's going on when you convert sight into sound. And my colleagues all over the world, like Jamie Ward and Amir Ahmedi, have been running science experiments on these sorts of approaches. And by the way, the sensory substitution doesn't have to be through the ears. Another version is called the brain port. And this is a little grid. It's called an electrotactile grid. It sits on your tongue and gives little shocks. So you have a camera, and that video feed gets turned into these little shocks on your tongue. It feels like pop rocks in your mouth. And blind people can get so good at using this that they can throw a ball into a basket, or they can navigate a complex obstacle course. They can come to see through their tongue. Now, that sounds completely insane, right? But remember, all vision ever are these electrical signals coursing around in your brain. Your brain doesn't know where the signals come from. It just figures out what to do with them. So my laboratory set out some years ago to solve sensory substitution for people who are deaf. And we wanted to make it so that the sound from the world gets converted in some way so that a deaf person can understand what is being said. So with my graduate student, Scott Novick, we built a vest. Now, this is not a normal vest. This is a vest that zips up tight around the torso, and it has 32 little motors on it. And these are vibratory motors like the buzzer on your cell phone, but 32 of them. And they're distributed pretty evenly around your waist and your back. And each motor represents a different frequency of sound from low to high. And by breaking up sound in this way, this is the same thing that your inner ear does, a part of your inner ear called the cochlea. So we have essentially transferred the cochlea to the torso. So it captures sound and turns that into these patterns of vibration. So some years ago, we started to test this in conjunction with the deaf community. Our first participant was a guy named Jonathan. He was 37 years old, he had a master's degree, and he had been born profoundly deaf, which means there was a part of his umvelt that was unavailable to him. So we had Jonathan wear the vest and train with it for 4 days, 2 hours a day. And by the 5th day, he was pretty good at identifying the words that were being said to him. So you say the word dog, and Jonathan feels a pattern of vibrations all over the vest, and his job is simply to write on the dry erase board what he thinks the word might have been. And by day 5, he could get this mostly right. Now, we had trained him on a limited number of words, what's called a closed set, but when we switched to a new set of words, ones he had never heard before, he was able to perform well above chance, and he learned more and more quickly with every new set. And this suggested he wasn't just memorizing some answers, he was actually learning how to hear with the vest. He was translating the complicated pattern of vibrations into an understanding of what was being said. Now, he wasn't doing this consciously because the patterns are too complicated for that, but his brain was unlocking the meaning of this. And by the way, this is just like you listening to this podcast. You're not thinking, oh, Eagleman is saying some high frequencies and now some low and some medium, so that must be S sound. Instead, you've just practiced hearing your whole life, and eventually you become pretty good at using your ears and your brain. But when you were born, you didn't know how to use your ears, but your brain looked for correlations, things that went together. So you would watch your mother's mouth moving, and you get spikes coming down your auditory nerve, and you figure out that those go together. Or as a baby, you clap your hands and you get a different pattern of spikes coming down your auditory nerve. Or you bang on the bars of your cage, or you babble with your mouth. And these all correlate with particular patterns coming in along this nerve. And eventually, these patterns become what philosophers call a qualia, which is a private subjective experience of hearing. You don't have to think about what all the spikes mean. They just get translated into a direct perceptual experience. Okay, so back to the vest. So we tested the vest with lots of participants in the deaf community. And in fact, we even built a miniature vest because it turned out that one of the people we were working with had a daughter who was born deaf and blind. So we made this little miniature vest for her, and it picked up on the sounds of the world and translated this into patterns of vibration on her skin. And so her grandmother took her around the lab and touched her feet on things and said, this is hard, this is soft, this is going up, this is going down, and so on. And this allowed the little girl to tap into a larger part of her umvelt. Then we made a smaller version of the vest, just a chest strap, and we began testing that with some other children. But eventually, we were able to shrink the whole system down to a wristband. And that opens up the technology for a much larger population. And we spun this off of the lab as a company called Neuroscience. And one of our first users was a wonderful guy here in the San Francisco Bay Area named Phil. And we videoed him talking in sign language about what the wristband meant to him. So I'm going to quote him here as a translation from the sign language he used. He signed, quote, "It makes me feel a natural connection with everyone around me. Sometimes I perceive, wow, I can tell what a sound feels like if someone calls my name, or if there's some kind of noise nearby, or my dog's barking, or even my wife calling me from far away, Philip, I feel her call my name and I go to her." So we tested lots of people who were deaf in the Bay Area, and people reported things to us like, I'm picking up on running water or birds or the oven timer. And when wearing it at work, I had a really good experience. Like when people were talking in the room, I could feel what they were saying, and it helped me lip read better. And as a quick side note, we went to interview lots of people who are deaf, and I came to understand that lots of deaf people live in nice apartments in one particular location, which is right next to the railroad track, because the sound of the howling trains passing by doesn't register with them and bother them, so they can live comfortably in a steeply discounted apartment that's perfectly nice, but people who are hearing don't want that apartment. Anyway, back to the story. Users started telling us that they were picking up on things that they didn't even know existed, like that microwaves beeped, or that their car blinker made a clicking sound, or that if they accidentally left the air blower on at work, that it was making a noise. Or for that matter, the loudness of toilets flushing, or that they had left the sink running. And they started feeling things like the laughter of their children on their skin. And they were able to distinguish which child was talking and which of their dogs was barking. And with time, people just get better and better at picking up the sounds of the world as patterns of vibration on their skin. And with one of our users, I asked him, what was it like when he hears the dog bark? Does he register, oh, there were just vibrations on my wrist, and so now I have to translate that? That must have been a dog barking. And he said, no, I just hear the dog barking out there, which sounds crazy, right? But remember, that's all that's going on with your ears. You hear the sound out there, even though it's actually happening in here, in your head. Now, after we were years into this project, I began to discover that the idea of converting touch to sound is not even new. I found a paper from 1923. There was a psychologist at Northwestern University called Robert Galt, and he heard about a deaf and blind 10-year-old girl who claimed to be able to feel sound through her fingertips. And so he was skeptical, and so he ran an experiment. He stopped up her ears and wrapped her head in a woolen blanket, and he put her finger against the diaphragm of a device which converted his voice signal into vibrations. So Galt sat in a closet and spoke to her through the device, and so her only chance to understand what he was saying was from the vibrations on her fingertip. And what he reported is that it worked. She was able to tell what he was saying through her fingertips. And in the early 1930s, an educator at a school in Massachusetts developed a technique for two deaf and blind students. Being deaf, they needed a way to read the lips of speakers, but they were blind as well, so that couldn't work. So the technique consists of placing a hand over the face and neck of the person who is speaking. So the thumb rests lightly on the lips and the fingers fan out to cover the neck and cheek. And in this way, they can feel the lips moving and the vocal cords vibrating and even the air coming out of the nostrils. And by the way, because these two original students were named Tad and Oma, this technique is known as the Tadoma technique. And thousands of deaf and blind children have been taught this method, and they can obtain proficiency at understanding language almost to the point of those with hearing. So the key thing to note for our purposes is that all the information is coming in through their sense of touch. And in the 1970s, the deaf inventor Dmitry Kanevsky came up with a 2-channel vibrotactile device, one of which captures the low frequencies and the other the high frequencies, and these two vibratory motors sit on the wrists. And in the 1980s, some other people came up with things like this too, which all demonstrated the power of sensory substitution. The problem was that all these devices were too large, and they typically just had one motor or two motors, and they got too hot, and it was not practical for people to wear these. It's only now that we're able to capitalize on a whole constellation of tech advances to run this in a wristband in real time. And so I'm really happy to say that the Neosensory wristband is now on wrists all over the world. And what's cool is that this technology is a game changer, because the only other solution for deafness is a cochlear implant. And that's something that requires about $100,000 and an invasive surgery. But the wristband we can build for 100 times cheaper. And that opens up the technology globally, even for the poorest countries in the world. And that's one of the reasons we've been able to get this into underfunded schools for the deaf all over the globe. And we've had many wonderful philanthropists help us do that, because this is such a different scale of solution that's simple and inexpensive and takes advantage of a very strange principle of the brain, sensory substitution. And we've just released something else that's having real impact. It's a version of the same idea, but it's not for people who are deaf, but instead people who are having normal age-related hearing loss, which almost always happens in the high frequencies. which is why people who are getting older and losing hearing start having a harder time understanding women and children because their voices tend to be at a higher frequency. So we developed cutting-edge machine learning that sits on the wristband and listens in real time just for the high-frequency parts of speech. So for example, it just listens for an S or a Z or a B or a K, and the wristband signals in different ways each time it hears one of those speech sounds. And so the key is when you're losing your high-frequency hearing, your ears are still doing fine at the medium and low frequencies. Those are getting to the brain. The wristband is just clarifying what's happening at the high frequencies, and your brain learns to fuse these signals from your ear and from your skin. So it puts together what it heard from the ear with what it's getting through the wristband, and after a few weeks, people develop much clearer hearing. And as an interesting side note, people don't always notice that they're getting better, but everyone around them does. And if they forget to put on the wristband, they get yelled at. So that's an example of pushing some information into the brain via an unusual channel, while most of the information is coming in the normal way. And I'll also tell you something else amazing that we found, which is that the wristband works incredibly well for reducing tinnitus, which is ringing in the ears. So a couple of research labs had previously shown that tinnitus can be reduced from something called bimodal stimulation, which just means that you have sounds and you have touch that are synchronized. So that's two modes, or bimodal. Now, the previous research had done this by combining tones, beep, 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 with shocks on the tongue, bzz, and that worked to drive down the ringing in the ears. So we did the same thing with the wristband, and it works the same. And we've published our data on this, that people with tinnitus get clinically significant improvement. Now, why does something like that work? There are some sophisticated arguments and debates about why this works, but I think the simple explanation is that we're just teaching the brain what is a real external sound, because those get confirmation on the wristband. When you hear boop, 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 you're feeling bzz, 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 bzz. But the tinnitus, the internal beep, gets no verification on the wrist. And so the brain figures out that's fake news, and it drives it down. Now, we're doing all kinds of other experiments using the wristband for sensory substitution. So for example, we've begun to study this as a device for balance. So there are many people who have problems with balance because of their inner ear. They don't realize when their body is tilting. So in our experiments, they wear the wristband and they also wear a small collar clip. And the collar clip has a motion detector and a gyroscope in it, and it can detect your orientation, whether you're standing straight or you're tilting one way or another, and it just sends that information to the wristband. So you become aware if you're tilting and you know in which direction. So it goes bzzz when you tilt and bzzz when you turn the other way. And this is simply taking what your inner ear would normally do, and if there's something wrong with it, it's just sending it in through a different channel. And beyond deafness and balance, we're doing other things like working with prosthetics. So when somebody gets an amputation, they get an artificial leg, a prosthetic. And what we did is we put sensors on the leg so that you can feel the information on the wristband. So we're taking an artificial limb, and by putting angle and pressure sensors on it, we are restoring the sensory input that you would have from it just through your wrist. And that allows patients to learn much more quickly how to walk with their new prosthetic limb. Now, beyond sensory substitution, how could we use a technology like this to add a completely new kind of sense, to actually expand the human umvelt? For example, could we feed real-time data from the internet directly into somebody, and could they develop a direct perceptual experience? So some years ago, we did an experiment in the lab where a participant feels a real-time streaming feed from the net of data for 5 seconds. And then he's holding a tablet and 2 buttons appear, and he has to make a choice. He doesn't know what's going on, but he makes his choice and then gets feedback after 1.5 seconds. Now, here's the thing. The subject has no idea what all these patterns mean, but we're seeing if he can get better at figuring out which button to press. And he doesn't know that what we're feeding is real-time data from the stock market, and he's making buy and sell decisions. And the feedback is telling him whether he did the right thing or not. And what we're seeing is, can we expand the human umvelt so that he comes to have a direct perceptual experience of the economic movements of the planet? Here's another experiment, which I showed at TED some years ago in a talk. We scrape the web for any hashtag, and we do an automated sentiment analysis, which means, are people using positive words or negative words or neutral? And we feed that into the vest or the wristband, and this allows a person to feel what's going on in the community of millions of people and to be plugged into the aggregate emotion of giant crowds all at the same time. And that's a new kind of human experience, because you can't know normally how a population is feeling. It's a bigger experience than a human can normally have. And we're working on feeling signals that exist out there but are normally invisible to you. So imagine that instead of a police officer having to have a drug dog, they could instead feel the odors around them that they normally couldn't. So imagine building an array of molecular detectors, and instead of needing the dog with its huge snout, they can just directly experience that level of smell themselves through vibrations on the skin. And we're doing things with robotic surgery. So normally, when a surgeon is doing a robotic surgery, they have to keep looking up at the monitors to understand what's going on with the patient. But imagine being able to simply feel the data from the patient, the heart rate and the breathing and so on, simply feeling it as you're going and not needing to keep looking at the monitors. Another thing we've been working on for a while is expanding the umvelt of drone pilots. So in this case, we have the vest streaming 9 different measures from a quadcopter. So the pitch and yaw and roll and orientation and heading. And that improves the pilot's ability to fly it, because it's essentially like the drone pilot is extending his skin up there onto the drone far away. He's becoming one with the drone. He can learn how to fly it better in the fog or in the darkness, because essentially he is becoming one with the drone. Or something that's related to this is, imagine taking a modern airplane cockpit, which is full of gauges, and instead of trying to read the whole thing, you just feel it. Because we live in a world of information now, and there's a difference between accessing big data and experiencing it. And we're also exploring ways to expand your body to a different location. So imagine that you feel everything that a robot feels. So you send an avatar robot on a rescue mission into a place that's very dangerous, like after an earthquake with collapsed buildings and dangerous chemicals, and you feel what the avatar robot is feeling. So you can close the feedback loop between action and perception. And we're interested in using this for the military to reduce friendly fire, which is when a person gets killed just because one of their colleagues makes a mistake and shoots them. So with our chest strap and some encrypted position information, you can tell where your friendlies are in any moment because you're feeling them. You know their location right on your body. Like Fred is off to my left because I can feel a slight vibration, but now he's getting closer to me, so the vibration gets more intense. And now I know that Steve is behind the wall over there because I can feel him moving around even though I can't see him. And Tom is behind me back there. You don't have to rely on vision because you're feeling where everyone is. So with one of our engineers, Mike Parada, we built a version of this and we demonstrated it by turning to fiction. We had our vest make a cameo on the show Westworld. So if you saw season 2, episode 7, the storyline is that private military contractors drop into Westworld to take care of these out-of-control robots called the hosts. And we set this up so that the military contractors in the show are wearing our vests that let them feel the location of the hosts on their bodies. And that's how they know exactly how to target them. So as they're moving around, they can feel, oh, there's a robot over there, and there's a robot on the other side of that thing, and there's a robot in the dark over there, and they can aim at them appropriately. Now, as it turns out, all the military contractors eventually get killed, so the vest is not necessarily going to save your life if things really hit the fan with robot consciousness, but that's a different episode. And we've used this same concept for people who are blind. We set this up in collaboration with some colleagues at Google who have LiDAR in their offices. LiDAR is like sonar, but with light. And so with LiDAR, you can know the location of everything and everybody moving around in the offices. And we tapped into that data stream and we brought in blind participants and they could feel where everyone was. So if there's someone on your right, you feel a vibration on your right. And as they get closer, it gets more intense. And as they go away, it gets less intense. And you can feel them moving around you. And you can even feel when they're walking around behind you, which is better than sighted vision. And on top of that, we also added navigation. So our participants had never been to these offices before, but we type into the system a particular conference room to go to. And the person then feels on their vest a buzzing on the front. So they walk straight and then they feel a buzz on their left and they turn left and then they feel a diagonal buzz and they know that the conference room is diagonally over there. And they were able to navigate this way on top of feeling who is around them. And so in this way, they're not getting real vision, but they're getting a lot of incredibly important information in a very simple way. And there's really no end to the possibilities on the horizon with sensory substitution and sensory expansion. One experiment we did involves using these smartwatches that can measure things like your heart rate and heart rate variability and galvanic skin response. And so we tapped into the API for that, and we put the data on the internet, and then you feel that on the wristband. So you can feel these normally invisible states of your body. But the interesting part is when you take the watch off and give it to someone else, let's say your spouse, so that now you are feeling the physiologic responses of another person. You're tapped into their internal signals. Now, I have no idea if this is good or bad for marriages, but this is an experiment we're trying because humans are at a point now where we can open up new folds in the possibility space. There are things we can experiment with to have new kinds of senses and bodies. And we can feel things like not only other people's physiology, but things like entire factories or traffic patterns. In general, what this gives us is a new approach to data. Our visual systems are fundamentally really good at blobs and edges and motion, but they're limited in what they can attend to. They can only do one thing at a time, and that's not very good for high-dimensional data. But your body is very good at multi-dimensional data, which is why you can balance on one leg and you're getting feedback from all these different muscle groups. You're taking in high-dimensional data and dealing with it all at once. And with the right sorts of data compression, I think there's no limits to the kind of data that we can take in. We have about 70 different experiments running on this. And if you're interested, go to neosensory.com/developers, and you can see all the various cool projects that we and the community in general has done. So the possibilities are endless here. Just imagine an astronaut being able to feel the overall health of the International Space Station. Or for that matter, having you feel the invisible states of your own health, like your blood sugar and the state of your microbiome, or having 360-degree vision, or seeing in infrared or ultraviolet. So the key is this: as we move into the future, we're going to be increasingly able to choose our own peripheral devices. We don't have to wait for Mother Nature's sensory gifts on her timescales, because instead, like any good parent, what she's given us are the tools that we need to go out and define our own trajectory. So the question now is, how do you want to experience your universe? That's all for this week. To find out more and to share your thoughts, head over to eagleman.com/podcasts. Any questions or discussions that you have, please email podcast@eagleman.com, and I will be addressing those on future episodes. Until next time, I'm David Eagleman, signing off to you from the inner cosmos.